Are we starting?
I can edit it, so it doesn't matter.
I need to know when I need to stop cussing. Does YouTube care about any of that?
No.
Why don't show a nipple?
Yeah, you can get banned.
Okay. Oh, really? Man. Okay, so yeah, my name is Connor Herndon. I am now a first-year graduate student here at this wonderful Institute of Higher Learning. You'll probably see me a lot here because I live here. I also went here for undergrad, and now I hear that they don't teach Lagrangians at all, or Hamiltonians at all, a little bit of Lagrangians in undergraduate classical mechanics. And that's extremely important. So the point of this lecture series is to run through, very superficially, graduate level or upper undergraduate level classical mechanics, because that's not something that's apparently covered anymore, and it's very much required for the GRE, and it's just good to know because it's much easier than what they teach you in regular classical mechanics. I'm going to eat during this as well. So I'm not going to cover all of classical mechanics in this one single lecture because that would be crazy, that would be terrible. So I'm going to try to cover over the next few weeks. So if any of you have suggestions what you'd like to see, or if you don't like what I'm doing, tell me, or if you want to change the style of the presentation, please let me know about that. But right now, tentatively, I'm going to cover, at least today, calculus variations, because that's what I prepared for. If you want something else that fucking sucks for you. The next one, I'm going to talk about Lagrangians. I'm actually going to move into Lagrangians immediately, and then go into the Newtonian equivalents, and just do actually how to use Lagrangians and what they are. Later on, I'll go into symmetries and conservation laws, and how you can actually derive conservation of whatever you want due to symmetries, Noether's theorem, particular group theory, things like that. I'm going to go into, after that, Hamiltonians, the Lagrange transform into the Hamiltonian infrastructure of classical mechanics. And then after that, go into more fun, fancy things. This is where it should get more exciting, is canonical transformations and action angle variables and things like that. And then after that, I can just go ape shit and we can go into old quantum theory, because action angle variables is a very good starting point for going into quantum mechanics. But I'm not going to go after that because that'd just be terrible. So, so today is calculus of variations. Now, I'm not used to blackboards, so I'm very sorry if my handwriting is bad or if it makes a really loud squeaking sound. So, I have like a little bit of history here, so I'm going to straight up read this. So, in 1638, Galileo discussed in his discourse on two new sciences the descent of a particle from point A to point B. And he was like, if this is under the influence of gravity, what's the trajectory does this have to follow such that it gets to point B the fastest? So it was like, well, the stupidest approach, he'd be like, straight line, you're good. It just kind of rolls down this line and gets to that point. He's like, well, actually, it's a quicker path if you had a circle here. And you had an arc going that way and an arc going this way. And then he, I think he later posited that a circle would be the quickest path between the two things. Because it would be feeling gravity, it would be pulled down, and then eventually it would hit point B. So that was a problem. It's called the brachistochrone, if I pronounced that correctly at all. And that was a problem that he couldn't solve because they didn't have mathematical infrastructure at the time. So later, Johann Bernoulli, one of the 250,000 Bernoullis that did things, in 1696, in the Acta Eruditorum, it was the first scientific journal in Germany. It's kind of cool. He was like, given 2 points on the vertical plane, what is a trajectory that minimizes the time spent traveling from point A to point B? So he posed this problem to like all mathematicians at the time, and he tried to appeal to Newton's ego, which was apparently very easy. And he got Newton, Leibniz, another Bernoulli, himself, and then L'Hopital to all try to solve the problem. They all came up with different solutions, and they were all published. And Newton, I heard this anecdote from my high school teacher, was like mad because this problem actually took him like 4 hours to do, and that was apparently very long for him. But they all came up with solutions. And so, what was the problem that they were trying to solve in our more mathematical terminology of modern day? So we know that the distance that it's going to go is equal to the velocity times the time. So the distance that something will travel is its velocity times time. So if we were to integrate the distance divided by the velocity, which is going to be a function of the distance on this trajectory from this point to this point on the xy plane, the time spent is this interval. And we want to make this time the shortest. We want to get there as quickly as possible. But we also have to know what ds is, because ds is taken to be, I'll draw this out a little bit better. So this is our trajectory. ds is not in the dx direction, it's not in the dy direction, it's actually the direction along the path itself. So we have to come up with terminology for what ds is. So let's say we take this point here, I'll make this curve go up so that we have positive values. That. So let's take this point here and zoom way the fuck in. So we're looking at a straight line, because any curve, if you zoom in far enough, and it's well behaved, is going to be a straight line. So this is an extremely, extremely small section of this, and this is going to be ds. That's going to be that distance that we're looking at here. So the amount that it extends the x direction is going to be dx, and the dy directions, and then the y direction is dy. So just by Pythagorean theorem, we've got ds squared is equal to dx squared plus dy squared. So that means if we say that ds is equal to the square root of dx squared plus dy squared. Yeah, so weird, that sound. Okay, then we're just going to, don't tell mathematicians anything about what I'm about to do here. Let's see, so. All right, so we've got this now. So I pulled out a dx on both sides. We pull out a dx, now you've got dy squared over dx squared. And then let's just, now you can pull out the dx entirely out of the square root. Now you got this, and y is a function of x. That's just the derivative of y. So you just be like dx plus y prime of x squared. All right, so that's what we can say the infinitesimal ds is. And yeah, surprisingly, this works out amazingly, even though you just move things, these zero quantities around. So now you've got this. This is called the metric. Like Joe relativity and things like that. This is the Euclidean metric. So this is how you can explain like a distance metric, like a line segment on the Euclidean plane. But in curved space, it becomes much more difficult. But yeah, here we go. So now we've got this integral, this abomination here. That. And then we know that, just from conservation of energy, is that kinetic is going to have to be equal to potential energy at every location on here. We've got 1/2 mv squared is equal to mgy of x. So we've got that the velocity that we're trying to solve for here is the square root of 2gy. Okay, so now we can restate this integral in terms of only y. And we've got this now. All right, and we're trying to make that thing small. We're trying to find the trajectory y of x, the trajectory that this particle will follow on this curve, such that this integral becomes as small as possible. So whenever we're doing calculus, just regular calculus, you can find the maximum some point on a curve just by taking the derivative and setting it equal to 0, because you're just finding the extremum of that. But this is different. This is not just, this is not a function of some variable, this is a functional. A functional is something it's a function that takes in another function as an argument. So because of that, our lives are so much worse. So we have to do something entirely different. It's called calculus of variations. It's a completely different branch of mathematics. And as any good physicist, I learned the bare minimum necessary to do the physics. So if you actually know any of the math that I'm going to be doing wrong here, keep it to yourself for now, but tell me after the video is off. So that was a long amount of things. Hopefully by the end of this lecture, you can take the tools that I'm about to teach you and solve this brachistochrone problem yourself. I would have done it myself here, but I realized I had made a mistake, and I'm not going to try to redo it in front of a camera and you can hold live. Math's hard. But yeah, hopefully you learned something useful. All right, so here's where the good stuff is. This is delicious. It's going to be rough, but bear with me here. It's just a lot of math. But this is something that you would have learned in Classical Mechanics 2 if you take the undergraduate version, and Graduate Classical Mechanics 1 if you end up taking that as well. I suggest you don't look into calculus of variations yourself unless you just really like math. So let's say we've got a function f, and this function is a function, its derivative, and x itself. So what this means is, so normally, if you have some sort of configuration space, that's the space upon which all of your trajectories follow. That's like the space on where all your solutions are. Like you got a little guy here, and he's going to move along this trajectory. This is called Q. It's your configuration space. So this is a function of something on the tangent bundle of the configuration space. That's just fancy words, but you can look them up yourself later. So what this means is that it's not only a function of every location on this configuration space, but also it's a function of all positions, all functions that are tangent to that position space at every point. Because it's, whatever, I'm not going to do that, that's not. Okay. So we want to find, let's say we've got some function null j, which is dependent on f, just like we had before. We go from x1 to x2 of this function, f of y of x, y prime of x, and x itself. And you want to minimize this thing. So what this means is that f can take any possible number of values between these points. Let's say we've got y, or x, and y. And we've got 2 points, x1 and x2. So what this means is that f can take any possible trajectory between these 2 points. So it could go this way. It could also go this way. It can go all the way up here and then come back down. It can do anything like this. So what we need to define now is, instead of a deformation of a trajectory within the same path, let's say when y, and you're traveling along the same path, this is y of x, you usually do like, dy, dx or something like that. It's the movement of your trajectory along the same trajectory, or the movement of your particle along the same trajectory, along some path. What we're looking for here in calculus of variations is not differences along the path, but the differences between paths themselves. So what we're looking for is this distance now is delta. Whoa, that's an awful delta. So d designates distance along a path, delta designates differences between paths. So we're trying to find the path that this particle can follow such that this integral is extremized, and so on. So there's a lot of math here. Would you like me to actually go through the derivation, or like cut it more quick and just go to the solution and then show application?
Derivation.
Oh, you are fucked up. All right, kids, buckle up. I usually like to just go to the fun stuff, but it's kind of important to actually know the derivation of all this, I guess, maybe. So we've got, I'm going to write exactly what I just wrote, what I just erased. All right, so we've got our function of y prime, and x. And let's say, so we want to generalize this y of x function to all possible families of y. And what I mean by this is what I'm about to write in math instead. So we want to create a function, big Y, of x and epsilon, such that it's y of x plus epsilon times eta of x. So what this means is that if we were to choose epsilon equal to 0, then y of x 0 is equal to y of x. So what this means is that, just as I had before, we've got 2 points, and if that's y of x, then let's say that we could add some perturbation of eta, something else. We've got some other variable function that we're adding to this. And this big Y will reduce to little y of x whenever epsilon is 0. So all we've done is just generalize the concept of this trajectory that we're following. Yeah. And we require that eta becomes 0 at these locations. So basically, yeah, we want it to still hit these 2 points, eta of x. So eta of x1 is equal to eta x2 is equal to 0. So that way, whenever we hit the 2 boundaries, if epsilon is non-zero, we still do reduce to y of x at those locations, those boundaries. And we're looking for we're looking for the extremum of this functional j of f. So what this means is that we're trying to find such that dj epsilon, and epsilon is equal to 0, is equal to 0. Which is the same exact thing as setting the first derivative equal to 0. We're just trying to find the extremum of this thing with respect to now epsilon. As we change epsilon, we want to just find the minimum or maximum, the extremum of this functional j. So what we can do now is, since we have that j of f is equal to the interval x1, x2 of f dx, I'm not going to write the arguments out, then we can just use, we can pull that derivative into the inside and into partials. So do you all know about like partial derivative expansion? You don't know. x1 to x2. And what you do is you have to take the partial, just by chain rule, is df dy times dy d epsilon. We're using big Y because we're now naming f to be a function of the bigger y rather than the smaller y, because we generalized it. We're trying to find the smallest trajectory. I should have been explaining that now. df d, I'm going to say prime dy prime d epsilon plus d of dx dx d epsilon. All of that. Yes. Okay, so sorry, to more specify what I was saying earlier. So this function we are now generalizing to be a function of all possible trajectories that you could take between x1 and x2. And we will assume now that y of x is going to be, the small y of x, is going to be the function that minimizes this. We don't know what it is yet, but we're just going to be like, this f of x is now going to be a function of the big y's. It's going to be a function of the big y's. And f, when big y reduces to little y, is going to be the extremum of this functional. So what I've done here is I just did, the partial or expansion of this. So the partial of f on y, partial of y on epsilon, it's just chain rule expansion, plus on the second argument, and then plus on the third argument. Ooh, so that's good stuff, huh? All right, so we can figure out what these derivatives are because we actually have an expression for what f is. So if we were to say that df d big Y is equal to, let's see, so, no, we don't have that one. We have dy d epsilon. I lied to you. This term here. Because we know what y is. So we're going to take that derivative with respect to epsilon. We have eta. It's just the partial with respect to epsilon, so this one goes away. And we also know this term, because we know that y prime, because y prime x epsilon is going to be equal to y prime x. Let's just take the full x derivative of both sides. That's fine because epsilon is not dependent on anything. Eta is a function of only x, and y is only a function of x, so y prime. And then we just say that dy prime d epsilon. Partial on epsilon, so this term goes away and it's only eta prime. Woo! So we have this guy, and we also have this one. And then x is not, it does not give a shit about epsilon, so this term goes away. X is not a function of anything. So that term is dead because partial epsilon is partial epsilon. So what we end up with is now this beautiful creature times eta of x plus df dy prime times eta prime of x dx. Substitute everything right. Yeah, because these two terms we don't know, df dy prime, but this term turned into eta prime, the other one turned into eta, and then the third term just disappeared. Okay, and we're also evaluating this thing when epsilon is equal to 0. So this is all epsilon is equal to 0. So when epsilon is equal to 0, big Y turns into little y. So let's see. Well, I'll just write the 0 on this side, on the left-hand side, because that's what the 0 is. So this now turns into df dy eta of x plus df dy prime Nothing funky going on here to an extreme amount. It's just when epsilon is equal to 0, the big y's down here now turn into little y's because that's what we defined as a function earlier. All right, yeah, woo. So this is two different integrals. We're gonna split this up into two. x1, x2. Left and y. So I'm trying to hit a bunch of steps because I want to make sure you all actually can follow what I'm going through here. So just split this up over addition. And what we're going to do with this term here is we're going to use integration by parts to split it up. And what that will turn into, if you, I hope you know integration by parts, I'm not going to go through it because I refuse to do math anymore, is this term, x1, x2, this integral only here, df dy prime, df prime of x, dx, may be split up into two different contributions. One is just the product between two things, and then one is the integral of something. Yeah, integration by parts is great. So what you get if you do that yourself boy, people keep coming in here, this stress me out. All right, so you get these two contributions to just the second integral here that we've done. All right, so luckily we have an answer to some of this stuff. So earlier I had defined eta of x as vanishing at the endpoints. Eta of x1 is equal to eta of x2 is equal to 0. It has to die. So we're going to kill that bastard. This is evaluated at x2 and x1. It does not matter what partial f on y prime is. He's dead at the endpoints because you just substitute those two in there. And this integral, the right integral here, turns into just negative integral of eta of x times d by dx of the partial of f on y prime. So now what we've got, if I just substitute that into here instead, we have 0 is equal to x1, x2, it's almost over, I'm so sorry. Partial f on y, eta of x, minus integral of x1 to x2 of eta of x, d by dx, partial f on y prime, dx. Oh yes, you can taste it, it's delicious. So now what we can do is we can pull, we basically integrate over both of these, this minus this inside part, and also pull the eta out. Just write it instead of saying. All right, yeah, chicken yak. So what we have here is that this integral has to be equal to 0 by definition, what we had said. It has to vanish, it has to be 0. So this is where the good stuff is. So that means that either eta of x has to be 0, or this has to equal that term. So df dy equals d by dx df by dy prime. So one of these two things has to be true. Luckily, eta of x is not always 0. It's an arbitrary function. I put no claim on eta of x except that it vanishes at the endpoints, x1 and x2. So this, when this isn't satisfied, this has to be true instead. So if we want a complete generality with this integral, we have to say that this always has to be true for this integral to be 0. And what this started with was that we started with the derivative of j with respect to epsilon is equal to 0. We were minimizing or extremizing this function. What we were doing is trying to find the extreme value of it. This could be a minimum or a maximum. And for that to be true, this has to be true. So what this is the Euler-Lagrange equation. So this is what, oh, it's beautiful. This is what you're going to be using for classical mechanics. Instead of having to worry about force laws and things like that, you can use the Euler-Lagrange equation. And I'll explain that next lecture, how you actually use that with Lagrangians and what this means and everything. But this is beautiful. This gives you the ability to minimize things. So you can use this to solve the brachistochrone problem, but I won't do that. What I will do instead is prove to you that a straight line is the shortest distance between 2 points. Because if you don't trust that, now you will. So that was the end of the extreme math, so you don't have to worry about that anymore. All right, so let's say that we have a real problem. Like, like so many problems that we don't know how to get from point A to point B in the shortest amount of time, and they're really, you can like see point B, and you don't know if you should just walk that way or not. So point A is located at x1, point B is located at x2. So what we want to do, again, as I've written before, is we wanted to minimize the integral of ds over your velocity. So let's say you're going to walk at a constant rate. It doesn't matter where you're going to walk. You're going to walk in circles or something like that. It doesn't matter. So this can be pulled out of the integral 1 over b from x1 to x2 and ds. So we're trying to minimize this this time spent. Luckily, earlier we have the ds for the metric. That is dx times the square root of 1 plus y prime of x squared. And now that's it. That's all of the thinking that we had to do. This is all of the thinking that we had done earlier. So this is just, we're trying to minimize the integral from x1 to x2 of that stuff in the integrand. This stuff, dx. So what we can do is just use Euler-Lagrange equation blindly. So this is f. That whole thing, anything that you have in the integrand that you're trying to minimize is going to be the f that I was talking about earlier. And if we want to find the extremum for this time spent, we need to just plug it in to the Euler-Lagrange equation. So you've got df dy is equal to d by dx partial on y prime. So what this means is that we have to take this thing, find the partial of it with respect to y, and then find the partial of it with respect to y prime, do all that stuff, set it equal to each other, and then we have our solution. So I don't know how you feel about taking a partial with respect to y prime or not. It's kind of tricky when I first saw that sort of thing. So what you can think instead is you can name y prime to be, I don't know, like the squiggle thing. And then later on you can name this to be squiggle is equal to y prime. Because, well, whatever. You can do some great stuff in math. It's excellent. So let's do this then. Just listen to me erase this entire board. Yeah. So, partial of f on y. Who can tell me, this is lecture style, who can tell me what is the partial of this thing, this entity, with respect to just y? The partial derivative, so only terms that are explicitly dependent on y. Well, yeah, what you got, Shumway?
Is it 0?
Yeah. Yeah, most of the time, like 90% of the time, the professor's asking you a question in class, it's
0.
It's like it's 0. It's really disappointing. Okay, so yeah, that's partial with respect to y. I'm just going to check stuff to make sure I don't mess up at some point during this. That would be terrible because I'm trying to find a straight line. Good. Yes, we're good then. All right, so then we're going to take this in baby steps first before taking this side. So the right-hand side, we have to find partial of f with respect to y prime. So this is partial y prime of 1 plus y prime of x squared. So 1/2, and if I'm going to do this by looking at my paper because I need to know my derivatives. 1 plus y prime of x squared to minus 1/2 times 2y prime of x. Oh, please God. Is equal to y prime of x times 1 plus y prime of x squared minus 1/2. Yeah, good stuff. All right, so now we take the full x derivative of that. All I'm doing again is just solving for the right-hand side, which point I'm going to set it equal to the left-hand side, which was 0. And this, I don't, okay. I'm going to look at it this time. I don't want to do this. Too old for this. Yeah, that. So we set this bad boy equal to the 0 up there. Good. So we got 0 is equal to, and then just reduce that a little bit. Y double prime of x times 1 minus y prime of x squared really trusting past self here. I'm sure he did math correctly. No, yes, 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 we're good. All right, good. So we've got that thing equal to 0, because all I did was I'm just forcing this upon this poor guy here. I don't even have to know what's going on here. It doesn't matter. That derivation I did earlier, don't matter. Just use this equation. All you have to do is set up your functional in terms of the integral of something else, plug that something else blindly into this, and you have the solution, an extremum of what you need. So that's all I've done here. And all I've got from all of that, the Euler-Lagrange equation, is this. So what does this mean? What does that mean? So that means this is true either when y prime goes to plus or minus infinity, because we need 1 minus 1. And that'll happen when we're traveling directly, like either up or down. Or basically, as much as we can. We're not going toward point B at all, and we never will. That is an extremum of our possible trajectories. We're not going to make it. It's the maximum possible time taken to get to point B, and you will never make it. You suck so bad. There's also y double prime of x is equal to 0. And when that happens, that means that the derivative y prime of x is equal to constant. We can say that constant is like m. And then just using another constant of integration, we have y of x is equal to mx plus another constant of integration b. And we see that the solution could either be y prime goes to plus or minus infinity. This is where you have to think. Either you can walk as far away as possible from the point you want to go, or you can walk directly there. And that's why calculus of variations is useful. So obviously we knew the answer to this problem here. But in many situations it's not nearly as obvious. This calculus of variation can be used to solve systems like a soap bubble, for instance. Soaps try to minimize their surface area, I believe, something like that. So if you can write the surface area as an integral of something, just how much it's extending in different directions and things like that, and just blindly plug it into this. No question at all. Just find an integral for the surface area of a bubble, given some boundary conditions, plug it into this. You have the shape of the bubble. Okay, that's really hard though. Doesn't sound like it. And we've also just proven that the shortest distance between 2 points is a straight line, which is pretty cool that math can do that as well, I guess. Because that's a pretty deep question, I feel. It's like the easier a problem sounds, the more hard it is. Because like proving things that can equal other things is like the most impossible thing to solve. So yeah, that's calculus of variations. That's it. I think, yeah, this is very early for ending, but that's good because this is the shitty lecture. The ones in the future will be actually using this stuff. I'm sorry that you had to deal with this because this is the infrastructure upon which classical mechanics is built. So next one, if you're interested, it will be on Lagrangians and how to use, how to express this in some way that makes sense in classical mechanics. And then just blindly throw this at it. And then you get the answer to everything. It's fantastic. It's so good because you don't have to deal with forces anymore. I don't even believe in forces. Because you can start with something called Lagrangian, which maps something, the tangent button on the real line. All you do is you just start with this thing. You define something called the action, which is the integral of the Lagrangian, dt. What you do is all you have to do for classical mechanics to solve pretty much anything is just define something we know is the action, get this Lagrangian, and then, oh man, we want to minimize the action between 2 points. I don't give a shit. We'll just put it right into this. Now it's partial L on Y, partial, all this. So that's really good. So that's what I'm going to try to do next lecture. If you're interested in other things, please let me know. Is there any topic in classical mechanics maybe you were particularly interested in? Okay, then good. You're just going to ride with me on whatever I'm going to do. And maybe next lecture I'll include how to derive conservation laws themselves, because that's pretty deep. It's insane, because you can do that. How powerful. So, yeah, that's just a tidbit of the future for all that. Yeah, I'm done now. Unless, Zane, do you want me to say anything else? Cool. All right.
Any questions? Yeah, no? Cool.